All right, so linear programming is a way to maximize or minimize values within a set of constraints. All right, I realize that what I just said made no sense at all, but let's think about it. If you went to the store with $120 and you knew that you could buy jeans for $30, only in a dream world, right? Jeans for $30 and shirts for $15 each, say. And what you wanted to do is maximize the number of articles of clothing you could possibly buy, because there are a lot of combinations that you could spend or that you could purchase and still have only spent $120. I could buy one pair of jeans and one shirt and have less than $120. That shirt certainly fits. But I could buy two pairs of jeans and one shirt still having less than $120, or two shirts and two pairs of jeans puts me at what, $60, $90. So what is the maximum number of articles of clothing that I can buy? Linear programming will tell you all the possibilities, and then it'll help you maximize your purchase. So in a nutshell, that's what linear programming is. It's just figuring out within a set of constraints being that I only have $120, that jeans cost $30 and shirts cost $15. If I can write an equation that explains the money I spend, then I can use linear programming to find the best value. Okay, so first we have some vocabulary, and these are all vocabulary words that you need to put on flashcards for studying. You need to know these words. So first, there is a function called the objective function. So the objective function is written in a funny way. Part of it will look very familiar, but the other part will seem really funny. So let's use this as an example. If I were to let x equal the number of jeans I bought or could buy, and y equal the number of shirts, we would write the objective function like this. The function of x and y, just writing a point in there where you're going to substitute x for x and y for y, equals, well, $30 for a pair of jeans, 30x, plus 15y to represent what I spend on shirts, plus imagine I had to pay a parking fee, and that was part of my 120, so say $5.50. All right, so this would be the function that I would use to say how much I'm spending altogether. Okay, and I'll use this to maximize or minimize my purchase. Now, when we write this in general forms, it looks like this. All right, so this is my first, the first step is determining an objective function that works for the scenario. Then in the situation, you're going to find that there are constraints. I don't like the way that looks. So a constraint might be something like, I've been given a limit. I'm allowed to have, or X has to be less than or equal to $60, meaning that the most jeans I could buy would be 2 pair. Okay, and I might have a Y constraint that I'm required to have to purchase at least 4 shirts. So Y would have to be greater than 15 times 4, 45. So I might have a list of constraints that I'm going to use to find out the best purchase or the best value in my objective function. Okay, so let's just start working on some problems to see how to work with linear programming situations first, and then we'll do a couple of examples that show in the real world how it's used. So we're given a objective function, or I guess I should say an objective function, the function of x and y equals 2x plus y. And we don't really know what situation this is. I gave us an example of buying things at a store, but we don't know what this example is. We're not given that, but we are given the constraints. X plus y has to be less than or equal to 5. So when I add x and y together, I can't get a number bigger than 5. 2x plus 3y has to be less than or equal to 12, just another constraint. X is greater than or equal to 0, and y is greater than or equal to 0. All right, so these are all inequalities. The constraints are inequalities because they're giving us variable outputs. If I buy 2 pairs of jeans, then the number of shirts I'm going to buy varies or depends on. So they're all inequalities, so let's graph these inequalities. So let's start here. Y equals, our x plus y is less than or equal to 5. So if x is 0, y is 5. Remember, when you're going to graph, you just treat it like it's an equals. So when x is 0, y is 5. And when y is 0, x is 5. And since since it can be equal, it's less than or equal to, then I'm going to use a solid line. So the next equation, again, I'm going to just use cover-up method. If I let x equal 0, then y equals 12 divided by 3, which is 4. And if I let y equal 0, then x is 12 divided by 2, which is 6. So if I put this line together, with the other line, I can see that they have a place where they intersect. And because we're talking about inequalities where equal is included, I would have to decide, well, if I put in 0 for x and y, then I'm going to get less than 5. So I know for my first line, we're looking at these values. My second line, 2x plus 3y, again, if I put in 0, I know I'd be looking at these values. And then the next two lines are pretty easy. They're just the x-axis and the y-axis. All right, and so the values for my x-axis and y-axis are greater than and greater than. So that means that the region of possibilities is all of this area here. Any point, any value, including on the lines that I use to find this region, any value, any combination of x and y that I plug into my objective, my objective up here will be a true statement. It'll fit the criteria or the constraints. So if I were to plug in 1, 1, for example, and let's go ahead and do that. Let's just say this is 1, 1. So I'd have the function, or the f of 1, 1, equals 2 times 1 plus 1, which equals 2, 3. Okay? So in this case, a value that makes a statement true would be the point 1, 1. But we want to maximize or minimize this value or this point. So really, what we want is one of the vertices. The vertices always give us our optimization points. And in this case, we're looking at these vertices. Oops, I made a little mistake. I'm sure you guys saw it. Let's put that there. It doesn't change the problem much because if I include this less than part, then I'm really just adding a little bit here. Okay. All right. Fix now. So I want to look at the vertices. So what are the vertices of these lines? All right. Well, let's just start working. We know that this vertex, because that one was easy, that's the one we graphed when we used cover-up method with this equation. So we know that that vertex is at x equals 0, y equals 4. And we know this vertex is at x equals 5, y equals 0. This vertex is super easy to find. It's usually 0, 0. This last vertex, that's the one that's going to be tough. But we know that that's actually the solution to a system of equations, and the two equations we used are these first two. So let's just use a quick elimination. X plus y is less than, I'm going to use equals because all I care about is the vertex point, is less than, or is x plus y equals 5. And then I'm going to use substitution method because I think this one's going to be super easy to do that way. You could use a matrix for it, but you don't need to. So I'm going to solve for x. I'm going to plug it into this one. So I have 2y plus 10 plus 3y equals 12. Combining 2 and 3y, I get 5y. And then subtracting 10, I get 2. So y equals 2/5. And then I'm going to plug that back into this one, and I get x equals 2/5 minus 2/5 plus 25/5. So x equals negative 2 plus 25 is 23/5. Oh, that's ugly. So I have x is 23/5 and y is 2/5. Luckily, I only have to operate with that once. Now, we want to determine which of these vertices is going to maximize our objective function. So that just means I have to plug it in. So I already did the f of 1, 1. Let's figure out the f of, well, let's go ahead and do 23/5 and 3/5, or 2/5, excuse me. So that equals 2 times 23/5 plus 2/5, plugging in x for x and y for y. So that equals 46/5, or 46 plus 2/5, which is 48/5. And just so I kind of know what the number is, 5 goes into 48 times. Oh, 5 goes into 45 9 times, so 9 3/5. So the value on my objective function for this vertex point is 9 3/5. Let's just work our way around 0, 4. So 2 times 0 plus 4 equals 4. So this is less than this. 0, 0. 2 times 0 plus 0 equals 0. And last but not least, f of 5, 0 equals 2 times 5 plus 0, which equals 10. So now we can say what our max and our min is. Our max value is 10 at the point 5, 0. And our minimum is, what's our minimum? 0 at the point 0, 0. All right, so let's do a quick overview. We have an objective function. We're looking for the x and y pair that either maximizes or minimizes this function under a set of constraints. We graph all the constraints, and then we choose the region that is bounded by all of them. So this region is less than, it makes this equation true, but it doesn't include the region that makes this equation true, right? So you find the place where there's a common bound. And now we can say that every single point in this region will be a solution, or will be a solution to the objective function. And by solution, I mean all of these criteria are met when I choose this value. So if I choose any point in this region, plug it into my objective function, all of these constraints will be met. But I want to look at the absolute maximum value for this function and the absolute minimum. Maximums and minimums always happen at a vertex, and I find out which is which by just plugging all my vertices into my function, taking the smallest value is my min, the largest value is my max. And so I can say what combination of x and y I would have to choose in order to get a maximum or minimum value on that range. Now, these are used in business and economics all the time, but I am losing my voice, so I have picked out a really nice Patrick JMT video that will explain a real-world situation. So look for that one right underneath mine.